Hello. In this video, we're going to look at the line of best fit, which is a very useful application of linear equations. So we're going to start by looking at the scatter plot. Scatter plot is a graph just used to determine whether there's a relationship paired between data. And so they show trends in data. So each of these, this is kind of hard to read, but this is age and height. So the x-axis is age and then height, and would be actual individuals who represent each dot. So each dot represents a person. And you can see that as someone gets older, their height tends to increase. Now, if you think about this in the real world, well, let's think about our data size here. Are you really going to grow that much between like the age of 22 and 28? Or maybe these are just taller people, right? Like this. So this doesn't necessarily represent you would question whether this represents a correlation between whether you're 18 or 28 in your height, or if maybe this is just people who are taller. Where if the ages were younger, if the ages were like 2 to 12, you would definitely think this would suggest some kind of correlation. But nonetheless, this data does show a trend. You could draw a line that kind of fits through this data. So let's talk about positive correlation. So positive correlation is as independent variables increase, dependent variables increase. So this is an example of positive correlation. What type of slope of this? This is a positive slope. So if the line you draw through the data, that's pretty close to all the data, and there are more technical ways to defining that than just pretty close. But that's all we're going to say right now as we introduce this idea. So if all these points are pretty close to the line, then and it has a positive slope, we can say there's some correlation, and the type of correlation is positive. So the independent variable is the x values of the domain. The dependent variable are the y values of the range. Some examples of this: temperature and bathing suit sales, or another common one is like temperature and ice cream sales. Or if you go the other way, like as temperature goes down, well, I guess that would be negative correlation. Never mind. Age and height, like I said, this is especially true in your developing years until you're, get to be 16, 17, 18. And then height and weight also, as height goes up, typically weight goes up because there's more of you. Okay, if it goes down the other way, so if it's negative correlation, the line we draw through is has a negative slope, or it's going down. Some examples of age and recess time at school: as you get older, your recess time goes down. Temperature and snow shovels sold. So like as it gets colder, typically you sell more snow shovels. And then it's also true, like if you think of like temperature and hot chocolate sold at an event maybe. And then time spent working and time spent watching TV. So the more time you spend watching TV, as this increases, or more time you spend working, the less time you will have to watch TV. However, with a lot of data, there's no correlation. So here, like you couldn't draw a line. Like if you drew here, that doesn't really make sense for the line. If you drew here, it doesn't really make sense. The line would probably be like somewhere just flat almost. And that would mean there's no correlation between the two variables. So age and eye color, height and number of siblings, it kind of just, you can think of any kind of random things, and a lot of times there's no correlation. And so that is the types of correlation: positive, negative, or no correlation, the ones we're looking for anyway. So here is some data. So this is the year and the number of tornadoes. And so we're looking for some kind of correlation between this. So the years are considered the independent variable and go on the x-axis. So this is x and this is y. Now you could, if you have time is almost always an independent variable. And sometimes you have to look at the whole situation to determine which one is the independent variable and which one's the dependent one. But the independent one is the one you're going to try to control, and the dependent one is a result of the x value changing. Okay, so let's go ahead and plot these points. And they don't have to be exact because obviously we're estimating here. This is by 200, so maybe let's write that in: 200, 400, 600, 800, and 1,000. And so 1950, we're a little over 200. 598, so 1955 would be here, and that's like at 598, so a little below. 1960 is just a little above 600. 65 is a little above 900. Wait, I wrote 100 instead of 1,000. And so let me see if I can get that kind of close there. 70 is 654, so that's down here. 1975 would be 919, so let's back up here, and it's a little above that dot, so I'm a little off. And then 866, 1980 would be 866, which would be up here. Okay, so now we want to try to draw a line through the data. Now I would recommend getting like a straight edge or something and like really playing around with the lines before you draw and see which one would look good. It's like if you get like a credit card or ID or something, or just a sheet of paper, you can kind of say, well, what if I drew it right here? Would that be close to the points or not? And these are estimations that we're using. You can calculate this with like a computer or something, or a spreadsheet, or even your calculator a lot of times. But we're just going to use an estimation. When you're drawing these, it might be handy to pick 2 points that the line actually goes through somewhere. They don't have to be the like beginning and end points, but then you have 2 pieces of data to write your equation off of. So I'm going to choose these 2 points, and that's kind of hard to see here, but I'll get that out of the way. So I'm going to say that looks like a pretty good line of best fit. But your answer will vary a little bit on these, right? Because if you didn't, you could say, well, maybe it's a little higher, and you pick something like above that point, which might actually be a better line. So it doesn't have to go through any points. It's the line that all of the points are close to. Okay, so rather, if you use these like actual points or not, you still have to find 2 points on the line that represent, or 2 points that are on the line to draw or write the equation on the line, excuse me. So I'm going to use this point, 1950. Whatever your points are, write your points down, 1950 and 201. And then this was the 1975 one, 1975, 1919. Now, but notice, like, I could use this point. I could say, well, I'm going to use this point instead. It looks like 1955, 400, and then this point here, 1965, 600. So this is it really is an approximation, and that your answers will vary. If you use 2 points, just kind of like practically speaking, that means you're more likely to get the same answer as somebody else, but the points will vary. Okay, so then let's calculate the equation on the line. So this is nothing new. If you know how to write an equation on a line, it's just where we pulled our points from. So we can find our slope. So m is y2 minus y1. Make sure y's go on top. And then 1975 minus 1950. So that's 25 years. And then I'm going to use a calculator for this just to make sure I don't mess it up. And 718. And so this will be a decimal more than likely with these approximations, because it's just more likely to end up that way. And that one's not too bad, so we won't round it at all. We'll just do 28.72. I would say if you have a decimal like it's long, a lot of digits, round to 4 decimal places is usually a pretty good number. Okay, and then we can use point slope form if we want, or y equals mx plus b. Let's do y equals mx plus b here because that's a pretty popular one. We'll use this first point. So y is 201, m is 28.72, x is 1950, and then plus b is what we're solving for. So when you multiply these 2 values, you get 201 is equal to 56,000. 0, 0, 4. And this makes me feel like I messed up somewhere. Oh, hold on. Yeah, never mind. This looks good. So then subtract this over. And so this is negative 54,803 is equal to B. So my equation, which we'll write up here so we can look at the graph, is y is equal to 28.72x, and then plus B would be minus 54,803. Okay, so a couple things. So first, does this look realistic? Okay, so we could say up 28 over 1, and that would be hard to check, but you could. It looks realistic there. But your y-intercept is something you can check. Does that seem real? Now, one thing to notice is it doesn't look like it on my graph, right? My y-intercept looks like maybe 100, and I have negative 54,000. But keep in mind, we use, in this example, we use 1950 for x. So 0 is 1950, almost 2,000 this way. So we'll have to keep going this trend until we get all the way to 0, which makes that number seem more feasible and more likely. Another strategy you could use with this is you could say where X is the year since 1950. And so you could make this 0, or make this 0 essentially on X, and then this would be 10 and 20 and 30. Hopefully that's not too complicated. And the bell is there. Okay, so here's another example I want you to try on your own. And I did this where I'm going to tap my finger for 25 seconds. And I want you to do this. It's a little tricky. I already did it off camera, so I already have my data. We'll fill in. But to get a stopwatch, if you need someone to help you write down or count, that's fine. And time yourself for 25 seconds and just tap your finger. You can do it. It's a little easier if you tap slow than fast. But tap your finger and see how many finger taps you have in 5, 10, 15, 20, 25. And then let's see if there's any correlation here. So we have, I did it and I got 10, 19, 29, 38, and 47. That's the number I counted. So then let's do this as 5, 10, 15, 20, 25. When you make a scatter plot, your tick marks need to be evenly spaced. If you have graph paper, that's better. And then I went up to, I'm going to go by tens. So 10, 20, 30, 40, 50, 60. Whoop, that one's a little low. Put 60 up here. And so this is time, and it's always a good idea to label it in seconds. And this is taps. Okay, so your tick marks, once again, equally spaced, and don't cram them in really close, right? Like keep them where they're spread apart so you can kind of tell what's going on. So we have a point here, 5, 10, 10, 19, 15 was 29, 20 is 38, and 25 is 47. And so this is almost fitting on an exact right line because my rhythm is just so good. And so if I draw my line there, it's like it almost fits exactly. Now, what would be different if you like sped up a little bit or slowed down in between times? Then your points how would they move? You know, think about that. They would be off the line a little bit. So, but I could really pick any points to compute this. I'm going to pick just to kind of do something maybe a little different. This one, 10, 19. And then I'm going to use 20, 38. So they look like they're on the line. It's not necessarily the first and last points. And I'm going to use the slope formula to find the slope. And then we'll do point slope form for this line. And once again, your answers will change. For practice, I would go ahead and pause the video and write my formula. But you can kind of compare it with yours and make sure the process is the same too. Your answers will vary. So let's see, that's 19 seconds there, and then over 2. So I'm just going to leave it as 19 over 2, or 9.5. And then I'm going to pick this point right here. So y minus 38 is equal to 19 over 2 times x minus 20. And there is my line of best fit, and just in time for the end of class as the bell rings. Okay, good luck with this, and let me know if you have any questions. Remember, as you work through this, your answers will vary, but they should be close, especially as you're working through problems from like a book or problems that were written from a set of data. Typically, like those questions are written so they're pretty neat, and you can find a good equation that's pretty close to what other people are going to find. But good luck with this, and reach out if you have questions.